Here's another problem with friction on an incline. We have a block, 1.8 kilogram wood block, launched up a wooden ramp that's inclined at a 40-degree angle with the horizontal. The block's initial speed is 14 and mu k is 0.2, and we want to know the vertical height the block reaches above its starting point. So first let's address the whole concept of the vertical height. Let's assume it starts here and it reaches some final point higher up the incline. We are looking for the vertical height that it reaches above its starting point, which we know this angle theta is 40 degrees. So if we can only get the displacement up the incline, we can quickly use trig to calculate the vertical height it rose to above its original height. So we know V initial is 14 meters per second. We know that once it gets to its maximum height, it stops. So V final is 0. We need to know the delta x so we can calculate the vertical height. And this reminds me of the equation v squared minus v0 squared is 2a delta x. However, we do not yet have a value for the acceleration. So we must use Newton's law to solve for the acceleration. So we draw a free body diagram of the block as it is moving up the incline. We have the force of gravity down the incline. We have the normal force, down vertically. We have the normal force normal to the surface. And since it's moving up the incline, the force of friction is down the incline. So we'll add our coordinate system, indicate that the velocity of the block is up the incline, and thus that's our positive direction. There's our vertical direction. And this angle is theta, so the angle that FG makes with the vertical is also theta. So acceleration is the sum of the forces over the mass, and we'll start first with the x direction. And the forces in the x direction are gravity, x component, backwards in the negative direction, and friction down the hill, opposite the motion in the negative direction. And we divide those both by mass. And so the gravity in the x direction is opposite the theta, so that's going to be negative mg sine of theta. And the friction force, friction is always equal to mu times the normal force in the kinetic case. And the normal force is opposite and equal to the y component of gravity, and the y component of gravity is mg cosine theta because the y component is adjacent to the angle that the gravity vector makes with our y-axis. So therefore, the force of friction is mu times the normal force, which is mg cosine theta. So we substitute that in, mu times m times g times cosine of theta, divide by the mass, and notice that since we have mass in both terms in the numerator, I can multiply top and bottom by 1 over m, and the mass cancels out, and the acceleration in the x direction is negative g sine theta minus mu g cosine theta. Oh, I don't have to divide by m. Too soon. There we go. And that's negative g times sine of theta plus mu cosine of theta. I just factored out a negative g. So that's negative 9.8 meters per second squared times sine of 40 plus 0.2 times cosine of 40. And when I plug this into my calculator, I get negative 7.80. meters per second squared. So now I can substitute that value, negative 7.80 meters per second squared, into my equation for kinematics. So v squared minus v0 squared is 2a delta x. That's 0 squared minus 14 squared equals 2 times negative 7.8 meters per second squared times delta x. So delta x is 14 squared on my calculator, divided by 2, also divided by 7.8, and I get delta x is 12.6 meters up the incline. So this is 12.6 meters in that direction. So I want the opposite side. I have the hypotenuse. So sine of 40 degrees is the opposite side, h, over the hypotenuse, 12.6 meters. So h is 12.6 meters sine of 40. On my calculator, that's 8.08 meters up the incline. Now I'd like to solve for part B, and I'm going to need a little bit more space. So I'm going to scroll down. I want to know what speed does it have when it starts back down, when it slides back down to its original starting point. So I know it's starting from rest at the top of the incline, so v initial is 0. And I want to know v final. And I know the distance it moves down the incline now is 12.6 meters. We solved for that in the previous part. And all we need is the acceleration down the incline. Now, some people might think that the acceleration is going to be the same thing as it was in the previous part, but it is not. No, not the same acceleration. Because in this particular case, I now have gravity still down. I now have normal force still perpendicular to the hill, but the velocity of the block is down the incline, so the friction force has changed direction. It is now opposite. So I now have two forces that are in opposite directions, the x component of gravity and the friction force, whereas before they were in the same direction. So I need to solve for a new acceleration. So I write my coordinate system in here, and I can see that the forward force in the direction of the motion, the acceleration, the forward force is the force of gravity x component, and the backward force is friction. Now we've done a lot of this already before, because we already found the force of gravity in the x direction, that's still mg sine theta, and the force and the friction force is still mu mg cosine theta. I just need to substitute them in here. So force gravity x, still mg sine theta, force friction, still mu mg cosine theta, and still all divided by mass. So now I can cancel the masses out. Once again, mass doesn't matter. And I can get that the acceleration is g times sine of theta minus mu cosine of theta. In other words, 9.8 meters per second squared sine of 40 minus mu cosine. Mu is 0.2. Cosine of 40. Notice that this is 4.79 meters per second squared. I want you to notice that this acceleration down the incline is much less in magnitude than the negative 7.8 up the incline. That's because the two forces on the way up the incline are in the same direction, in the negative direction, and the two forces on the way down, gravity x component and force friction, are in opposite directions. So on the way up the incline you have a greater magnitude acceleration, or deceleration as the case may be, and on the way up you have on the way down you have a lesser magnitude of the acceleration. So now I can substitute that back in, 4.79 meters per second squared, into my equation. V final squared, or V squared, minus V initial squared is 2a delta x. I'm solving for V final. V squared minus, starts from rest, is 2 times a, 4.79 meters per second squared, times the distance, still 12.6 meters back down the incline. And a little bit of calculation later, I get that the velocity at the bottom of the incline is 11.0 meters per second. I want you to notice that this is less than the original velocity. The original velocity on the way up the incline was 14 meters per second. So this is less than that original value. It has lost velocity due to the backwards force of friction. So our final answer for part B, with what speed does it return to the bottom of the incline? That answer is 11 meters per second.